Hello everyone, thank you so much for joining us today. My name is Victoria Getz and I'm a Senior Marketing Coordinator at 2H Offshore. I want to welcome you all to our webinar today entitled Why Minimum Facilities Platforms Are the Fastest Route to First Oil for Shallow Water Developments. Before we get started, I would like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we will go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. And with that, I'm very happy to introduce our speaker today, Ben Andrew. Ben is a director at 2H with 14 years of specialist engineering experience in design and numerical analysis of conductor-supported platforms, deepwater production, and drilling riser systems. He has held project management and technical lead roles on projects from concept through to detailed design based out of London, Leiden, Houston, and Kuala Lumpur. So now I will turn things over to Ben to get us started.
Thank you, Vic, for the warm introduction. Good morning, afternoon, evening, everyone. I'm excited to be here today speaking on this topic, and I hope you'll find the information useful. So, what are we going to talk about today? Well, I'll start by talking about why we might want a minimum facilities platform, and also clarify a bit about what we mean by an MFP or a minimum facilities platform, because there is some variability in what people mean by these terms. I'll then talk a little bit about how, in our view, you should go about delivering a minimum facilities platform, and certainly how we go about delivering them. And then we'll finish by pulling all that together with a recent installation example to show how it works in practice. So, why would we want a minimum facilities platform? Well, the first thing we're trying to achieve is to reduce our transportation and installation costs. And the way we normally go about doing that, where possible, is to use a jack-up drilling rig for as many or all of the operations as we possibly can. That jack-up rig is already needed for the field development to drill the wells, so why not avoid additional mobilization, demobilization costs by using it to install a platform if possible. In some cases that may not be possible or practical, in which case we want to make sure we're using the lowest specification installation vessel that we can, again in order to keep those costs down. And in terms of installation, we're simply looking to reduce the transportation payload as much as possible, again to keep the costs of the vessels down. So one way we do that is through cost-effective structures and facilities. So this gives two benefits. First of all, it enables the reduced T&I costs by allowing you to use small vessels and allowing the rig to perform the installation operation or the low-spec installation vessel. But also it reduces the fabrication tonnage itself, which may in turn open more local yards to being able to fabricate those structures. In terms of the facilities, the motivation is to focus on only delivering fit for the intended purpose equipment and so on, and not to allow topside growth to make the development impractical. And finally, but perhaps most importantly, we're looking to deliver early production. And the way we prefer to deliver this is, first of all, through delivering the project very quickly, but secondly, through pre-drilling of a fast-track substructure. Often the substructure of the platform is the quickest to deliver in a short time frame. And if it's installed with the rig can crack straight on with drilling the wells and installing the surface trees. You can see this in the image bottom right of the slide here, prior to the topside equipment turning up. And secondly, we try and do as little engineering as possible by using simple standardized design and simple fabrication in order to minimize the time taken to deliver that substructure to the field. So what do we mean by a minimum facilities platform? As I say, this term is used to mean a number of different things in the industry. Well, the way we see it is there's a range of different sizes and complexities of platform, going all the way from a freestanding conductor, essentially just a well on a stick, through monopiles where maybe there's some additional strengthening around that conductor, through to a tripod system, a wellhead platform, and a minimum facilities platform, just before you get to a full jacket structure. And from a 2H perspective, our solution for tripods, wellhead platforms, and minimum facilities platforms is typically the conductor-supported platform or the CSP Plus, which I'll talk about a bit in a minute. But what do we mean in terms of equipment and complexity here? Well, there's 3 examples at the bottom of this slide that work through the range. On the left, we have the simplest wellhead platform. As it happens, this one shown here is a retrofit system that was used to convert an exploration well drilled with a jackup into a production well by installing a couple of small structures. But this could be designed from the outset rather than retrofit. It's got maybe just the one deck allowing access to the wellhead. It's probably just producing the fluids and exporting them directly through a hose to somewhere else for processing. The topside weight here is unlikely to exceed maybe 60 tons. That's a very basic platform, of course. Moving beyond that to more of a wellhead platform, we're talking about maybe 1 to 3 decks rather than just the single deck. Production of somewhere up to 5,000 barrels of oil per day. Again, we're providing wellhead access, but now there may be some manifolding and maybe some flow metering. Again, though, the well stream export is just via a pipeline. We're not doing any processing on a wellhead platform. That's being performed elsewhere on an FPSO or a sister platform. And the top side here is maybe more of the range of 60 to 200 tons. Beyond that, we get to the full MFP, if you like, which is almost certainly 3 decks, maybe talking more like 10 to 20,000 barrels of oil per day. It's doing much the same as the wellhead platform, but maybe with a little bit of extra on there in terms of chemical injection and maybe a little bit of process equipment. If we're talking about processing equipment here, we're talking about test separators, crude stabilizers, etc. Nothing much more than that. And if we do start talking about that, the topside weight is maybe creeping to the upper end of that range to 500 tons to 1,000 tons of topside weight. So that's the range of minimum facilities platforms we're talking about here. They are lightweight in terms of equipment, and most importantly, they are normally unmanned installations. There's no accommodation on here, but they do include much of the usual E&I, process, mechanical, and safety equipment that you'd expect. So I mentioned that the 2H solution to this is generally to go down the conductor-supported platform route. So what do we mean by that? Well, a CSP uses the wells themselves to form part of the structural structure of the platform. So the wells are forming the legs of the platform. Typically, we'd have between 3 and 9 legs on the upper bound. That may mean you have more wells because there is the option for dual completion or splitter wells to be used within those legs. And the number of wells isn't necessarily the same as the number of legs. You may have a mixture. For example, the image in green on this slide, 4 of those legs are structural, but there are 6 splitter wells. So you have 6 conductors, you have 12 wells, but you have 4 structural legs. And then the substructure itself isn't just those conductors. There may well be templates of certain sizes or complexity and a mixture of those with free spans. Essentially here in shallow water, you may be able to get away with just the conductors, like the 10-meter example shown on the image on the right. But as you move into deeper water, you'll need more in the way of a substructure to brace those legs. The primary reason for that is to stiffen the structure to ensure we have an acceptable fatigue performance, an acceptable extreme performance, and make sure there's no issues with compressive instabilities on the legs. Eventually, in the deepest waters, beyond, say, 70 meters, it may be that you need a full substructure. That's when we start to talk about a mini jacket or a CSP Plus. It's still a very small footprint platform in order to enable installation with a drilling rig, but it now has a more substantial jacket all the way to the surface. In addition to the structural elements, the substructure would incorporate all the usual things you'd expect from a platform, like riser and conductor guides, installation aids, access, boat landings, etc., boat impact protection for risers, and so forth. One question when it comes to conductor-supported platforms is always, what are the limits of those? And unfortunately, it's not a particularly simple question to answer, but this slide sets out some of the challenges that you reach if you try and push them beyond their natural limit. So in terms of topside weight, something in the 50 to 100 tons is very easy to engineer typically. Once you get to 400 tons, that's sort of the natural limit of a CSP because it's where you reach the limits of the rig's lift capability. So beyond that, things start to get a little bit more complicated. That may involve post-installation of some equipment, two-part lifts, for example. Things can be done. But the 50 to 400 tons is the normal range, or 500 tons. Beyond that, things get a little more challenging. In terms of water depth, again, for between 5 and 55 meters, is very standard and typically very easy to engineer. Beyond 55 meters, things may get more complicated. You may start to need that full mini jacket structure, and beyond that, you may need to start having some skirt piles in order to improve the overturning resistance of the foundation. In terms of environment, an important point to highlight here is that these platforms are primarily driven by their fatigue performance, their long-term performance. So when we talk about the environment, we really are talking about the long-term environment. If you have a benign fatigue environment, then these platforms tend to be easier to engineer. If you have a more severe fatigue performance, environment, then they tend to be more challenging. Individual extreme events are less of a concern for conductor-supported platform design. And then in terms of number of wells, anything between 3 and 6 wells would be very standard. A 6 leg, I showed an example earlier where we have 4 structural legs and 2 additionals. Beyond that, things get more complex in terms of splitter wells, but that complexity really isn't around the structural design. The complexity is around the well bay space for the additional valving. So what do we mean in terms of equipment? Well, some examples are given here. Of course, this isn't comprehensive and there is variability, but it gives an idea of the sort of components that we might have on a minimum facilities platform. You can see mechanical equipment there, electrical equipment, very little in the way of process equipment. The other thing you may note is quite a focus on electrical systems here, and the focus there is to help ensure that these platforms are largely unmanned, certainly normally unmanned installations. We're trying to make these as much as possible minimum maintenance and no-touch platforms that can be relied upon to work remotely. And for that, electrical is better than using, for example, diesel systems. Coming back to the main benefits, one of the things we're trying to achieve here is efficient transportation and installation in order to keep those costs down. So as I mentioned earlier, rig installation is very helpful for this because it allows you to use the existing jack-up rig that you have in the field already. You have to mobilize and demobilize, you have to use for drilling operations to do the installation. In addition with that, it allows you to streamline installation and drilling activities. And you can sort of see here from the image just to the right of the text, an example where a substructure has been installed. The drilling rig has then performed some drilling operations. You can see 2 surface trees there on the completed wells, and then the topside can be lowered into position as soon as it is ready. So the rig could drill 1, 2, 3 wells to whatever level of completion makes sense before installing the topside, and then complete the remaining drilling operations through the topside. So that also helps to take time out of the installation schedule. Of course, if we're going to use a rig to do the installation, then we need to make sure we think about that when we're doing the design. And this is really key, that when designing these structures and designing the installation, we're thinking about rig standard operations. This is unusual for a rig, so we want to make things as comfortable for them as possible. So examples there are using threaded connectors that they're familiar with for the piles, sticking with standard foundation methods, for example, drilled and cemented or driven piles for the foundations. I mentioned earlier that in some cases it may not be practical to install all components with the rig, and an example there is where the topside weight gets to a level at which the rig cannot lift and skid the topside. An example image is shown on the right there. That may be where we need to use a barge to install the topside, but it may well still be possible to use the rig for the substructures and the drilling operations, and then we're only using the barge for the later stage once the topside is ready. So moving on to early production, the second or third pillar of the benefits of these. The whole design philosophy is driven around achieving that early production, and key to that is keeping the long lead equipment off the critical path. The example I'll show later evidences this, but an 8 to 9 month schedule from kickoff to hookup and commissioning is entirely achievable for a fairly substantial minimum facilities platform. And the sequence is, as I've sort of mentioned earlier, that we want to deliver that minimal substructure. We keep it as small as possible, as quick and as easy to fabricate in local yards. We then ship that and install it, ideally with the rig at the field location, and then the rig gets on with its pre-drill and well drilling operations and completion operations. After that, the minimal topside can be delivered. Again, we keep this simple and as quick to deliver as possible, but typically the long lead equipment for that topside is what drives the schedule more than the structural fabrication aspects. And when that's ready, it arrives and it can be installed with the rig or with a heavy lift barge before hookup and commissioning operations are performed. And then drilling can continue for the remaining slots thereafter. So how do we achieve a design like this? Well, firstly, we need to make sure that our structures are efficient. And in order to do that, we need to make sure we're doing efficient structural engineering using finite element analysis techniques. That's all built on classical structural analysis, for example, using SACs typically, but also based on understanding the nonlinear dynamic aspects of these platform designs. They are not large, stiff jacket structures. They are more compliant by their nature. So the understanding of what that means for the structural design of the platform is key to delivering an efficient structure. We want to use the well conductors for strength. They're there anyway. They have strength. Why not use them to keep the substructure size down? And that's what we're doing with the free spans, as shown on the right here. There's a substructure at the base, but between there and the top sides, we can live with a free span, just using the conductors themselves for the structural rigidity. In order to do that, though, again, we need to understand that within these conductors are our production wells. And that means we need to understand how that well engineering expertise ties in with the structural design. Second thing we need to do is focus on delivering a true minimum facilities platform, keeping that equipment manifest as minimal as possible, keeping the energy consumption as minimal as possible, and ideally keeping the systems all electric where possible. And we need to focus on a no-touch philosophy, a genuinely normally unmanned installation. That's partly around focusing on familiarity with delivering these minimum facilities platforms and understanding what is genuinely needed and what can be lived without. And finally, we need to make sure that the actual installation operation and transportation operation is efficient and integrated with the rest of the schedule. And that's about maximizing the flexibility we have in terms of the vessels we can use and understanding the capabilities of those vessels, in particular of the rig. So a close collaboration with and understanding of the rig operator, his concerns and worries is important to being able to deliver these platforms successfully. So we do all this as much as possible using a standard approach. We have standard components that we want to use to construct these things, but a bespoke design for each application in order to make it work and genuinely optimized for that particular field, for that particular rig, for that particular range of available vessels. In terms of the structural design, I mentioned earlier the substructure design is typically driven by fatigue considerations for these conductor supported platforms. So that's the first piece of work that we get involved with. That allows us to size the conductors, select the connectors, which may also be long lead items. It allows us to come up with the overall arrangement of the platform. In parallel with that, we work the installation procedure. There's no point designing a platform unless we're confident it can be installed by the intended rig or the type of rigs available in the region. And thereafter, we move into the more traditional jacket design activities, if you like, of looking at the strength capacity, structurally designing the substructures to take the extreme loads, designing the foundations to take the overturning loads, and so on. We do look at boat impact. That's often a question with these conductor supported platforms, is the criticality of their design for boat impact considerations without a full jacket structure. So we do look at that. Of course, these structures do not have the same level of boat impact resistance as a traditional jacket would have, but they have more capacity than people often expect. An example of that is shown in the graph down the bottom there, where the green region is the combinations of boat mass and drift speeds that can be accepted. These sort of structures are actually fairly compliant, so in a boat impact condition, they can deflect, they can absorb quite a lot of energy without damage to the well, and checking the denting of the conductors and making sure there's no integrity threat to the wells within is again critical to their design. Finally, some topics around seismic analysis if we're in a seismically sensitive region. Again, these platforms can work in seismically sensitive regions. They're typically not design driving. So I said that I'd bring this all together at the end by looking at a recent installation. So this is a platform that was installed in Southeast Asia recently by 2H Offshore. In this case, although it was fairly shallow water, it was a full jacket structure with the substructure reaching all the way up to the top sides for client preference reasons. So this was actually transported on a fairly small support vessel in a horizontal position and was upended by the rig. So you can see the transportation in the top image here. In the bottom left, this is a view from the rig with the transportation vessel below and the platform substructure being upended on the trunnions at the rear of that transportation vessel. So this is being lifted with the drill string and some soft slings while it's being upended from the back of the transportation vessel. In the middle at the bottom there, you can see now the structure is fully suspended from the rig's drill string and the transportation vessel is departing. And in the final picture there, it's been lowered to the seabed and the rigging has been slacked off. So that substructure is now installed and ready for the conductors which form the wells, but also which form the foundations to be run. So here are some typical conductor installation pictures. You can see on the left there that we're using standard rig technology in terms of threaded connectors for this technology that most rigs will be familiar with and will be comfortable with. In this case, they were driven to depth, but they can be drilled and cemented as well, depending on soil conditions. And then a rough cut is performed, as you can see on the right there, in order to then connect the conductors, the foundations, to the platform itself. The rig then skids between the different slots and runs each of the conductors, welds them in place and cements them. That then means the substructure is now stable and supported and structurally reliable, ready for drilling operations to commence while we wait for the topside to be ready. So then the topside itself, and you can also see a boat landing / protection frame being transported here in the top left hand picture. So that's all now been brought along. You can see this is a little bit later in that bottom left hand picture. You can now see that two of the wells have been installed, drilled and completed, and the trees installed on the substructure, and the topside is ready to be lifted in. Again, you can see there that we have some slings attached to a hook on the base of the drill string, ready to lift the topside. So the rig skids out, picks up the topside, transportation vessel departs, and the rig skids back, and you can see on the top right there, again, it's now landed that topside on top of the substructure over those two existing wells, ready for the structural connections to be made up. And here's the finished platform. You can still see the legs of the jack up there, but you can now see the 3/4 deck topside landed on its substructure. You can see the boat landing just behind it as well. So that's a typical example. They don't all go this way. As I say, it depends on the rig, it depends on the specific field, the size of the topsides and so on. But it's a typical example of how this works. So in terms of timeline, and again, this is the timeline for the particular case I just showed you. It's approximately 8 months from kickoff to commissioning, and it breaks down quite nicely into quarters of the year. In the second quarter of the year, the engineering is essentially conducted and the start of fabrication. So start of April is when the work was kicked off. Substructure steel first cut in mid-May, approximately 6 weeks after start, and that's where we can achieve that through standard components that we're using here. Topside first steel is a bit later, and then as we move into Q3, we're delivering the substructure, sailing it out to the field location and installing it by the 13th of September. So from kickoff through to substructure installation is less than half a year. Thereafter, the rig can perform its drilling operations while it waits for the topside to be available. In this particular case, they were fairly simple, shallow wells, so 2 wells were drilled in between that 13th of November date and when the topside installation was performed in mid-October. So the whole topside installation was complete in late October, and hookup and commissioning was completed a month later. In terms of offshore time, substructure installation took a little over a week. Some of the breakdown is given there. The largest operation for substructure installation is conductor piling, and it's worth bearing in mind that that's also work that would need to be done for any traditional well conductors anyway, in many cases, either drilling and cementing or piling operations. So yes, it will take longer with a structural foundation, but some of that time is saved in terms of well drilling. Then the drilling operation took place, and then the topside installation itself was a matter of a couple of days to prepare and install the topside. So overall, we've got less than 2 weeks, even with some margin in there, of additional rig time to install the platform. The rest of the time, the rig can continue with its high-value operation of drilling. So to conclude, minimum facility platforms can deliver early production. They can deliver significant reductions in transportation and installation costs, and they can deliver cost-effective structures and facilities, both to enable that reduced transportation and installation bill, but also to enable local yards and reduce transportation costs. In order to deliver this, we focus on using the right installation vessel or rig, and in particular making sure we use ones that are available and easily available in the region. We make sure we deliver a truly minimal facility platform. We avoid unnecessary growth in the topside complexity. And we focus on optimizing those delivery schedules, in particular focusing around the drilling operation, which is the high value activity for the rig. And that's all enabled by the use of genuinely minimal structures and installation through the rig. We keep our engineering smart to make sure we deliver optimized designs that are installable and do the job they're needed to do without being oversized. And ultimately, this all comes by using, as much as possible, standard approaches and components, but optimizing them in bespoke design for the specific application that they're needed for. So that completes my presentation.
Thank you so much, Ben. We've already had quite a few great questions from our audience, so I will go ahead and get started asking those. First question, roughly when do you need extra piles on top of conductors?
So in fairly shallow water, certainly anything up to 55 meters, potentially up to 70 meters in some regions, the standard well conductors are all you need. In particular, you're limited by the rig drilling envelope in terms of the footprint of this thing, which keeps it fairly compact. Beyond 70 meters or in harsher environments is where you may start to need some skirt piles in order to increase the overturning resistance of the platform. This is all doable, just adds a little bit more complexity.
Okay, great. Next question. Why don't you make all those structures braced all the way to the top every time?
Yeah, so you saw from the particular installation case that I showed there that if you have a fairly tall substructure, you need to perform an upending operation in order to lift it. And that's essentially because of the lack of height or headroom between the installation or the transportation vessel rather and the rig's drill string. So what that may mean is there's a limit to how tall that substructure can be. So you can either transport it horizontal, which is an option, but even easier than that is to keep the structures compact and small enough that they can be lifted in a vertical position. And that's generally our preferred route, but that means you can't be too tall and therefore you need to have some free spans. It's also possible to have a number of substructures that could be stacked, is another approach around that. But in general, unless there's a specific need for the structure to go all the way to the surface, we would try to avoid it.
Okay, next question. I think this is a question from the video. What are the pins on the side used for?
I'm not totally clear on what the pins on the side are referring to, I'm afraid. So that I might need a bit more clarity on that question.
Okay, and maybe whoever asked that question can reach out to Ben afterwards, and he can go into more detail for you on that one.
Yes, of course. Sorry, I'm just not clear on
Okay,
that one.
yeah, that's okay. We'll just move to the next one. If you weld the conductors at the top, why do you need to also cement those to the jacket or substructure?
Yeah, so essentially a lot of the stiffness of the system is coming from those conductors, and we need a nice rigid connection between them and the jacket legs. It's not that different to many skirt piles on jacket structures. We like to grout the annuli between the conductors and the sleeves in order to increase the structural rigidity of the system and improve the load transfer between the foundation and the structure.
Okay, next question. What topside footprint can you typically handle?
Sorry, can you ask that again, Vic? Missed the first bit.
Sorry, yeah. What topside footprint can you typically handle?
Okay, yeah, thank you. So the topside footprint, again, is largely driven by that stage in the installation where the rig reaches out beyond the substructure and lifts the topside off the transportation vessel. So if it's being installed through a rig, then the topside is typically limited by the skidding capacity of the rig. Typically something like 12 meters in that dimension would be the limit. You can go wider than that in the transverse direction because that constraint doesn't apply. So something like a 12 by 16 meter topside footprint would be achievable. Larger may be achievable if you're not using a rig for the topside installation because again that envelope stops being relevant.
Okay, and you might have already asked this question, but answered. But what is the max water depth in which you have installed minimum facilities?
So the maximum water depth in which we've installed them, I believe, is around 90 meters. That in particular. So another option that I haven't talked about here as well is there's an option for these platforms to be linked to an adjacent production facility, either another platform or a jack-up acting as a MOPU. In those conditions as well, you can get some additional structural support. But in either case, 90 meters is, I think, the deepest we've installed one.
Okay. This is another question from the images you showed. What are the components of the 3 decks, and does it contain the oil processing equipment?
So generally speaking, we're not including full processing equipment. These platforms are generally designed to act as, say, minimum facilities platforms. Once you start putting serious process equipment in there, full separators and so on, the topside weight starts to increase beyond the point at which it makes sense to use a conductor-supported platform. So at that point, you probably are looking at more like a conventional jacket solution. So the processing equipment would typically be housed either on another platform within the field. So this might be an expansion of an existing field or an early production system for a field, or it might be housed on an FPSO or similar as well.
Okay, next question. Oh, sorry, yeah. Next question. What are the specific requirements needed for the rig used for the installation?
So again, there are no specific requirements. I mean, the rig needs to be skiddable. It needs to be able to lift structures with its drill string, but I mean, that would be met by any jack-up rig, essentially. Again, it very much depends on the application. If we're in deeper water, we'll need a larger footprint, so a rig with a larger skidding envelope would be beneficial. If the topside weight is larger and the intent is to install it with the rig, then that rig will need to have a higher lift capacity in terms of its draw works and its drill pipe. And there's a combination there between the ability to lift and the ability to skid that weight. But for a smaller platform with a small topside, for example, the simple tripod wellhead platform that I showed earlier, a very low spec jack-up rig would be able to install that. So it's again a very difficult question to answer in the abstract. It depends on the specific development objectives.
Okay, and I guess a follow-on question to that, have you managed to remove the requirement for a crane on a minimum facility?
So I think most of the minimum facilities platforms, so sort of of the three types I showed more to the right hand side of that, the majority of those will have some sort of crane, although it may be limited to like a 5-ton davit crane or similar, rather than anything more substantial than that. Again, it comes down to specific project requirements, which I'm aware I'm saying quite a bit, but it is true because we want to only put on these platforms what's genuinely needed for that application.
Okay, another one, do you have any experience for installation of MFPs in water depths of 100 meters in the Gulf of Guinea in West Africa?
So in 100 meters, as I mentioned earlier, the deepest water depth in which we've installed platforms is around about 90 meters. So 100 meters is deeper than we've installed, I believe. I will check that offline and can revert on that one specifically. So specifically 100 meters, no, but the 90-meter design was robust for deeper waters. And we have performed engineering studies which show getting to 100 meters in those regions is achievable.
Okay. And I guess for your example that you went over, when was the rig selected? Was it during basic engineering?
In that particular example, I am not sure. I know that the installation design, the platform design, was for that specific rig, but exactly where in the sequence the rig was selected, I'm not sure. It was selected prior to the placement of the contract for the platform supply, though.
For the CSP insertion, what are the parallelism required / tolerances between the piles? Is there any contingency plan?
Okay, so I think this is a question around the verticality of the piles that are installed within the structure. So the structure itself will have fairly good tolerances from fabrication. We would include centralizers within the sleeves to guide the conductor as it's driven or drilled to depth. Most commonly, we drive these to depth, and they are sort of held vertical by the centralizers within the sleeves during the drilling operation. Typically, we're targeting within a couple of degrees of verticality for the conductors.
Okay, next one, how do you manage the interface between rig selection and MFP design?
So we work very closely with the rig suppliers to make sure we understand their capability. One of the challenges, for example, with doing it is that we need the rig to be able to lift some weights typically and then skid with that weight hung off, for example, when they're installing the topside or when they're installing some of the ancillary equipment like boat landings and so on. That is not a particularly standard operation for a rig, and therefore they aren't necessarily completely clear on what the rig's capabilities are. So understanding, kind of as I mentioned earlier on, understanding the capabilities of the rig, the concerns of that particular rig operator when designing the installation and designing the platform is key. I also mentioned earlier on the installation procedure work and the platform design work always have to go hand in hand. We can't design a platform and then figure out how to install it. We can't come up with an installation procedure for a platform we haven't yet designed. So the first stage of the design is to interface closely with the intended rig or potentially intended rigs, and work the design of the platform in parallel with that while understanding their restrictions in terms of what can be achieved with that rig.
Okay, what is the most severe site environmental conditions to date? Is it cyclonic?
Yes, so we have designed these for cyclonic conditions in Southeast Asia, and as I mentioned earlier, we are more concerned about the long-term fatigue environment than we are about individual extreme environments. These platforms are fairly compact, they have fairly small wind areas. They have fairly small footprints in terms of drag area, subsea. So extreme events are not so much the issue, it's the fatigue design of the platform that typically drives. So North Sea, more challenging, for example, but cyclonic conditions not necessarily a concern.
Okay, the next question. What is the typical range of payload for a MFP for 2 wellheads plus chemical injection package and a helideck?
Okay, so that is something I would prefer to take offline and make sure I come back with the right numbers for that rather than taking a stab at it online right now, I think. So I will take that question offline and get back on that one.
Okay, yeah, we can follow up with that question after the webinar. Okay, we've got time for a couple more. Can you make the substructure stackable?
Yes, absolutely. So I mentioned earlier on as well, it may be preferable to an upending operation if you do need quite a tall substructure, in which case we may ship multiple substructures either on separate transportation vessels or on the same transportation vessel. It makes it easier for the jack-up as well, a simple lift and lower of one substructure, then a simple lift and lower of the next one, with some kind of simple latching mechanism between the two subsea before the conductors are driven through the now combined substructure. So again, our preference is to avoid that, keep things as simple as possible, but as you move into deeper water or harsher environments and we need more substructure, we would look at the specific rig, we would look at the specific design requirements and take a view as to whether stackable or potentially upended is the way to go for that particular application.
Okay, have you designed any platforms for seismic loads?
Yes, we have, not for particularly high severity seismic loads, not highly seismic regions, but we have performed for low seismic regions in line with API 2GO in order to ensure the platforms are resistant to seismic events. And for those low seismic regions, the seismic events do not drive the design of the platform. Again, it's still driven by that in-place fatigue loading.
Okay, this will be our last question for today. How do you bring the riser or umbilical to the platform? Is it through one leg?
No, so the conductor or the platform legs are either purely structural or more commonly well conductors within them. The risers or umbilicals will be separate rigid risers or J-tubes for riser or umbilical pull-in that will be housed inside the footprint of the legs. Where we have structures, like where we have the template structures, they're protected by those. Where we have free spans, they may need some dedicated riser protection frames, which may be integrated with the boat landing to prevent accidental boat impact coming into contact with them. But there'll be separate structures run from the topside to the seabed.
Okay, great. Well, thank you, Ben, for all the information on the topic. That is all the time we have for today, but as we mentioned earlier, if we didn't get to your question, or if you would like to continue the discussion, please contact Ben directly using the details provided here. Thank you to our audience for your time and participation, and we hope you all found this useful and will join us for more webinars in the future covering a range of riser and subsea topics. Again, please look out for the recording of the webinar in your email in the next 24 hours, and we hope you all enjoy the rest of your day.